Welcome to lecture 13. In this lecture, we introduce eigenvalues and eigenvectors, and we look at some of its basic properties and couple of examples. Let A be an n by n complex matrix. That means A is a matrix in C n cross n. A scalar lambda in C is called an eigenvalue of A if there exists a non-zero vector V in C n cross 1 such that AB is equal to lambda times V. Such a vector V is called an eigenvector of A corresponding to the eigenvalue lambda. Let's look at one simple example. Take the matrix with rows 1 1 1 0 1 1 0 0 1. Then this has an eigenvector 1 0 0. So look at A multiplied with 1 0 0. What you get is 1 0 0 0. So therefore I can write this as AV equal to 1 times V, where V is the vector 1 0 0 0. So therefore 1 is an eigenvalue and 1 0 0 is an eigenvector corresponding to the eigenvalue 1. Given this, what can you say about 2 0 0 0? Is this an eigenvector? Now if if V is an eigenvector corresponding to an eigenvalue lambda, what can you say about alpha times V, where alpha is a non-zero scalar in C? Do you see that alpha V will also be an eigenvector corresponding to the eigenvalue lambda? That means corresponding to an eigenvalue we can have infinitely many eigenvectors. If you find one of them, you can find infinitely many of them. Let's look at one basic property of eigenvalue, in the sense that given a matrix, how do we go about finding this eigenvalue? That comes from the theorem. Let A be an n by n complex matrix. A complex number lambda is an eigenvalue of A if and only if determinant of A minus lambda I is 0. Let's first prove this and then look at its consequences. Let V be a vector in Cn cross 1. Let V be non-zero. Then V is an eigenvector of A for the eigenvalue lambda if and only if AV is equal to lambda V, or in other words I can write this as AV minus lambda V is 0, or in other words A minus lambda times I multiplied with vector V is 0 if and only if V is a non-trivial solution of the homogeneous system A minus lambda I times x, where x denotes the n vector with variables x1, x2 up to xn. So this says that V is a non-trivial solution to the homogeneous system. But when can this happen? We have already seen this. This happens if and only if rank of A minus lambda I is strictly less than n, and that happens if and only if determinant of A minus lambda I is 0. So therefore lambda is an eigenvalue of A if and only if determinant of A minus lambda I is equal to 0. Now look at this polynomial, determinant of A minus ti. Take t as a variable indeterminate, and look at this polynomial, determinant of A minus ti. This polynomial is called the characteristic polynomial of the matrix A. And the previous theorem says that lambda is a root of this polynomial if and only if lambda is an eigenvalue. Lambda is a root of this polynomial if and only if lambda is an eigenvalue. So therefore, given a matrix, to find eigenvalue, you compute this matrix, compute this polynomial, characteristic polynomial, determinant A minus ti, and then look for its roots. So given this A minus ti, determinant of A minus ti, fundamental theorem of algebra says that this polynomial has n complex roots. So the coefficients of the characteristic polynomial are all complex numbers, and therefore the fundamental theorem of algebra says that this polynomial has exactly n complex roots. The n is obtained by counting each root with its multiplicity. So the zeros or the roots of this characteristic polynomial are the eigenvalues. Now if you have if all the coefficients, all the entries of the matrix A are real, then this says that the characteristic polynomial is a matrix, characteristic polynomial is a real polynomial, and if you have a complex root, then we know that the conjugate of this complex root is also a root of this polynomial. So if alpha plus I beta is an eigenvalue of a matrix with real entries where beta is non-zero, then alpha minus I beta is also an eigenvalue of this matrix. Let's take one example. Let A be equal to the matrix with rows 1 0 0, 1 1 0, 1 1 1. Then the characteristic polynomial is determinant of this 3 by 3 matrix A minus ti, which is equal to 1 minus t the whole cube. So the zeros of this polynomial are 1 1 1, and these are the eigenvalues of A. Now how do we find eigenvectors? Apply A minus lambda I on the vector ABC and solve. So A times ABC is equal to 1 times ABC. Solve this system of linear equations. What you get is A is equal to 0, B is equal to 0, and C is in F, can be arbitrary. So therefore the eigenvectors are of the form 0 0 C, where C is a non-zero complex number. Now take this matrix A equal to 0, 1, minus 1, 0. Its characteristic polynomial is t square plus 1. So therefore its roots are I and minus I. So the eigenvalues of A are I and minus I. Now find out the eigenvectors. Solve the system of equations A times A B is equal to I times A comma B, and A times A comma B is equal to I times A comma B, and then solve them. What you get is, for eigenvalue lambda equal to I, we get A comma I A is an eigenvector for any non-zero A. And similarly for eigenvalue minus I we get A comma minus IA for A non-zero. These are the eigenvectors. The maximum k such that t minus lambda power k divides the characteristic polynomial is called the algebraic multiplicity of the eigenvalue lambda. Or in other words, if you take the characteristic polynomial and lambda is a root of this characteristic polynomial, then the multiplicity of lambda as a root of this polynomial, that's called the algebraic multiplicity. For example, if you look at example 2, the algebraic multiplicity of the eigenvalue 1 is 3. So we conclude this lecture here. We will look at more properties of eigenvalues, eigenvectors in the later lectures.